Hello class, here is today's lesson where you are going to be graphing linear and nonlinear inequalities. The emphasis is on nonlinear. We'll start with a review problem of what we were working on last week, and then we have some nonlinear inequalities to do down here. So a total of 6-ish problems for today's lesson. Let's begin. So down here, we start with a review. We have this inequality, it's linear. There's only one line for it. What color am I going to use today? Purple, why not? Actually, let's use black. So we have this line, there's a slope, there's a y-intercept, so that's what we'll put onto this graph. Let's choose 0 to be here. There's your x-axis. Let's call this my y-axis. 1, 2, 3. My y-intercept is here at -3. And then I'll be going, let's say, up 5. 1, 2, 3, 4, 5. Left 3. 1, 2, 3. But the other way I don't think I would have fit on this particular graph. I grabbed some kind of straight edge, which I have one along my table somewhere. Old credit card will do. And connect these two dots together. I look at my graph again and I see that it is the greater than or equal to sign, so that means I draw this solid line. Right? Why did it disappear? Go away. So I draw a solid line. Let's try that again. Solid line. Like that. And then I start some kind of shading. So now I test a point. 0, 0. Let's see if that makes this equation true. Is 0 bigger than or equal to -3? That's true. So then when I shade, it's going to be on this side of the graph. I feel like I'm going to do that a lot better. Let's make my highlighter huge. Yeah, that's going to be this whole side of the graph. Let's go back and answer some questions about these. What's the minimum number of points you need to test to know which side to shade? Just one. You may have to test 2 if you choose a point that's on the line. Why is 0, 0 such a convenient point? Just like with the zero product property, anything times 0 is 0. It makes for the math to be a lot easier, the arithmetic. Test the point 3/2. So with our equation, this is the x-coordinate, y-coordinate, or the x value and the y value. We have 2 is greater than or equal to, could be greater than or equal to, 3/5 times 3 minus 3. Following through with this arithmetic, we have -5 minus -3. 2 is bigger than or equal to -8. True. So whichever point 3/2 lies, +3, 1, 2, 3, 1, 2. So this point, 3/2, is also a solution. So that we've just confirmed which side of this line over here to shade. So any point can help you. This one involves a little bit more math, and that's okay. 0, 0 just makes for a much shorter time. That's our review problem. Now we move on to the new stuff. We have an inequality here, And on the right-hand side, you may recognize that we have a quadratic. And when graphing quadratics, it's going to be helpful for you to determine where the x-intercepts or the vertex is. Need 3 points. When I look at this, I can see that you can factor it. So that's drawing your box and the diamond, which we started at the beginning of distance learning and school before school closed. So we draw our box and our diamond. Here's x squared, here's 3. Together they need to multiply to 3x squared, and we have negative 4x's to work with when we add them up. So it looks like this. And so when factoring it, it looks like x minus 3 times x minus 1. By zero product property, 3 is an x-intercept, and so is positive 1. Next off, we need to figure out the vertex. So at this point, we have a choice. We can use the completing the square method, or we can use the shortcut, right, via axis of symmetry. So we did a lot of book work going over that. That's the negative b over 2a. So this only gets the x coordinate of vertex, which happens to also be your axis of symmetry equation. We look at this particular equation. We have b is negative 4, a here is positive 1, negative 4 over 2 times 1 gives us 4 over 2, so we know the x coordinate is 2. Solve for y. So 2 squared minus 4 times 2 plus 3. Four plus 3 is 4 minus 8 plus 3. Positive 4 plus 3 is 7. The vertex is at 2, 7. We have our 3 points, and that's enough information. Let's put 0 here. Draw our axes. Let's see, positive 3 and positive 1. Turns out I didn't need all this space. Vertex is at 2, 7. I feel like I made a mistake somewhere. 1, 2, and then positive 7. Yes, I messed up my signs, it appears. Let me check. 3 and 1, okay. 2 negative b over 2a, yeah. 4 divided by 2 is 2. 2, oh, negative 7, there we go. Wait. Negative 4, oh, I messed up here. Here's my mistake. Messed up my signs. So this part first gives us negative 4. Negative 4 plus 3, positive 3 gets us negative 1. There we go. So 2 comma negative 1 is down here. If you follow through with the axes of symmetry, looks like this. Our parabola at minimum looks like this. We could test another point, like you know here that this thing is your y-intercept. So you know that 1, 2, 3, it goes up here. Making use of the axis of symmetry, if it's 2 squares away going like this, it has to be another 2 squares away going like this, so you'll have this other point. It looks something like that. And we're just sketching. Gosh, magnifying glasses is rather annoying. Let's say it continues up like this, like that. And since we're working with inequalities here, you still got to test a point. So after we've graphed our parabola, let's test out 0, 0, just like when we did with the linear inequalities. Let's make this in red. Oh, we'll have a pink. We still got to test out a point. So let's test out 0, 0. So is 0 less than 0 squared minus 4 times 0 plus 3? 0 is less than 3? True. So that means we shade in this whole region. Thought I made it bigger. Apparently not. So everything that is not on the inside part of the parabola is now a part of our solution set. There's still just two regions here, the part inside the parabola and the part outside the parabola. Okay? That's the one difference between linear and non-linear inequalities. That's our answer there. A bit more work because the functions are a bit more complicated now. So what I've shaded in green, that is the solution to this inequality, y is less than x squared minus 4x plus 3. Here's your second problem for today. Review of how exponentials work. So as we're working through this problem, we think about, okay, this thing out here is your initial value, or y-intercept. This thing is your growth rate. When I look at this, since it's 1 point something, I also know that this is meaning a 15% increase. For this problem, let's go and graph this by putting 0 here. Okay, there's your x, there's your y. 1, 2, 3, 1, 2, 3, 4. We know that this thing is going to be one of our points. And then we can begin testing stuff. So maybe I'll choose, so what I'm doing is making a little table. We already know for 0, we get 4. Let's try positive 1. 4 times 1.15. We think about 15% of 4, still a decimal. 1.15 times 4, we get 4.6. We can test out 2. 1.15 times, times 1.15 times 4. This gets us 5.29. So it's rather steep. So 1, that's 4, 4.6. Let's call it right about here. 0.6, maybe right about here. And then for 2, it's 5.29, so a little bit past 5, like that. Maybe we'll go this way. Let's try negative 1. So anything to the negative 1 power, you write it as a fraction. 1.15 to the power of negative 1. We get 3.478. A little bit less than 4. Maybe it's right here. And then maybe negative 2. We test this out. 4 times 1.15 to the power of negative 2. We get just about 3. 1, 2, 3. And at this point, we kind of see the shape of our exponential. So with these 5 dots, you can see that it curves down, but never touches the x-axis. That's the idea of an asymptote. Oops, messed up my line. It has to be a dotted line because it is strictly less than. Okay. It never touches the x-axis. That's one of the special features of exponentials. And now we test. Let's test a point. We're going to test out 0, 0. So is 0 less than 4 times 1.15 to the 0th power? Is 0 less than 4? Yes? So that means we shade the side that includes 0. So it's everything over here. Okay, this whole region. So for exponentials, nothing much that's special. I made a table for it. You know how to use your exponents, use a calculator. I'll move on to our next one. Here we have something that looks rather complicated. I see that it's something squared, so I know it's going to be a quadratic. From the looks of things, it's kind of hard to tell, but this is actually a vertex form. I think this is something I underemphasized in our quadratics unit. So I'll write out the general equation for it. Okay. So here we have an a value of 1/4. We have, so vertex is at, let's see, 6, 3/4. We have a messy equation looking like this. I think it's a good idea to expand it and then use the quadratic formula. You don't have to. You could, well, I'm like thinking. You still need to do another point, and I guess we can test a point. The quadratic formula, we've seen enough. So for this one, let's think about trying to find, yeah, so you can make a table, guess and check kind of method. Standard form is going to be helpful. I don't think I've demonstrated that just yet. So what we know so far is 1, 2, 3, 4, 5, 6, and 3/4. Okay, this thing is going to be your vertex. So we can test out the point 0. So 0, and make an xy table. 1/4 times 0 minus 6 squared plus 3/4. So all this thing is equal to -6, 36. 36 over 4 is 9. 9 and 3/4. 0 is 1. That can even fit. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3/4. Alright, so it's off my graph. A little bit too high. That's still good. So I can make use of my axis of symmetry. In this case, it doesn't look like there's an x-intercept here, so I'm glad I didn't use the quadratic formula to figure that part out. How do I know? Because I know generally that my parabola is going to open something like this. I can tell because the a value here is positive. So if I go 6 units this way, I go off the screen, so I can't graph that. Okay, let's choose 4. 1, 2, 3, 4. 4 is, I hope, going to be a convenient number. 4 squared, -4 squared, plus 3/4. 16 over 4 is 4, plus 3 is 3/4. Yeah, that works out. 4, and 1, 2, 3, 4. 4 and 3/4. Dang it. The app that I use, it autocorrects sometimes, trying to recognize some shapes that I draw. But I don't really want that, like drawing a dash. I don't want a dash. So 2 away, it's at the same y coordinate, like that. 4 3/4. So, although kind of seems really off scale, doesn't it? 6 3/4. I'm like thinking, did I mess up my vertex form? No, that's right. So we have enough information. I think this point out here is kind of off scale. So 4, 5, 6, 7, 8, 9. Yeah, this one should be higher. 1, 2, 3, 4, 5, 6, 7, 8, 9, 3/4. A little better. Not really. Maybe like do this first. Like that. Alright, doesn't look the best. Hope you get the idea. Test a point. So now 0 has to be bigger than all this stuff. We know that from this equation here, that this thing is 9 3/4, which is false. So that means we shade the inside portion of our parabola. And notice it's a solid line because of this part. So the fourth example. Two shorter ones. Almost there. With this example, I didn't draw a graph paper because you don't need it. X and Y. So if your x coordinate is going to be, let's say here is +2, you have to be less than -2, you are going to have a dashed line here. Here's 1, here's -1, here's 2, 0. It's everything on this side of this vertical line. Okay, it may be hard for you to remember. Okay, if I just have x here, is that a vertical or horizontal line? In this case, think about it as a number line. Just focus in on this part right here. Okay, and it's exactly the same as what you've been doing before. Instead of drawing a dot, you draw a line that goes straight up, and it's dashed. So think back to your number lines, and it'll help you with orientation. Does it go left and right, or does it go up and down? For this problem with absolute value, we have to break it up into two inequalities. So the first one, simple enough, is y is less than 2x minus 1. Okay, you just drop the absolute value bars. The second one, flip sign and let's say the variable, y variable. So it look like negative y is now greater than 2x minus 1. That's how we graph inequalities, that idea of flipping it, because there's two equations here. In this case, we have two inequalities. So as we solve both of these two, we have to graph them. This one, we can multiply both sides by -1, we get this thing. Okay, so here are the two equations we have to plot. Let's put 0 here. I don't want that, let's put it over here. Okay. X and Y. So one's at -1, up to right 1, like that. Darn it, it should be dashed. And we test out 0, 0 here. Test 0, 0. Is 0 less than -1? False. So we don't include that point in our solution. We shade in this side for this particular line. Okay. Now for the other equation, let's use a different color. Let's use y is less than -2x plus 1. So now, oops, did I make a mistake? Yes, I did. No, yeah, I did. Darn it. Made a mistake. Got my slope wrong. I was looking at the wrong equation. So as I clean up, here's my y-axis. Here's x is +1. Let's go up to left 1. So it should be this, the purple equation. It's kind of easy to make these mistakes since these equations are so similar. Out of here. Come on. Alright. So now I got the correct equation. I'm going to test out 0, 0. Is 0 less than 1? It is. So for this purple equation, let's shade in this side. So you get the idea. Purple, purple. Now for the black equation, we will plot it correctly. There's your y-intercept. Come on. There's your y-intercept, -1. And I go up 2, right 1. There's our 2 dots. We draw our line that is positive. Come on. It's also dashed because it is strictly less than sign. We notice we have an x, and now we already tried out 0, 0. In this case, we will shade in the line that doesn't include it, so that's going to be this side. And we notice here, since both the overlap has to be our solution, our answer is in this area. Okay, notice you don't include the boundaries, but this red thing that I'm outlining is our solution to this absolute value inequality. And that's it for today's lesson. The only step that changes is you have to graph nonlinear inequalities, which does take some time.